So want to look at, this is a kind of a cool problem, optimization problem. Yes, sir.
You never answered that one riddle we had last week.
What was the riddle last week? It was the guard. Okay. Yeah, so here, let me pull it up. Hang on. All right, Kyle, you got the award for getting me off topic. That's pretty good stuff. Okay, flip charts. What day was it? Monday, last week. So I'm gonna guess it's that one. No. No. No, it wasn't that one. Shoot. There it is. That one, right? Okay, so what's the verdict here? You come to a fork in the road. You know that one fork leads to, that the two roads go to paradise or the land of misery. You don't know which was which. There are two guards there. One lies all the time. One always tells the truth. You don't know which is which. But you want to know how to get to paradise. What do you ask? You have one question to ask one of the guards. What do you ask? Yes, ma'am. Okay, right. So you say, okay, you just point to one of the guards and you say, okay, here's the two guards. Here's the two guards. If I want you to answer, I would say, okay, you tell me, where would he tell me to go? Where does he say paradise is? Right? You ever see why that works? Okay, right? Because what happens if Andy's the liar and Kyle's the truth teller? What's Andy going to say? He's going to point to the bad place, right? If Andy's the truth teller and Kyle's the liar, Andy's still going to point to the bad place. So you just go the opposite of whatever he says. Does that make sense? Okay, there you go. All right. Good. Good stuff. How many people got that? Okay. All right.
Just a little bit longer.
You just never know when you're going to find yourself in that situation. So I thought that was a good one to take a look at. Okay, on to calculus. Hey, what time's is it televised tonight, the volleyball game? Yeah. It is? Okay. 5:30? Okay. All right, so 4 feet of wire is used to, is it really televised? How do you know where to look for it? Like sometimes they do that stuff. It's all, okay, all right. Well, I'll figure it out. Last time it wasn't. Big Mike forgot to turn it on. Last time it was what? Big Mike forgot to turn it on, so it wasn't on the last one. Oh, okay. So what's the app? How would you do that?
You can just look it up. It's just the NFHS website, and it costs
okay.
You can make a free.
It's serious?
No, you can make a free account, and it's
Oh, okay. All right. Gotcha. Okay. All right. So we got 4 feet of wire here. Here's the challenge here. We got 4 feet of wire. We need to use the wire to form a square and a circle. Okay, we're going to bend it into a square. We're going to cut it and bend it into a square and a circle. We want to know how much of the wire should be used for the square and how much should be used for the circle to enclose. Let's do 2 things. Let's find how could we find the minimum area enclosed or the maximum area enclosed by the wire. Okay, so we'll do 2 parts to this. It's same table. It's like it's just one problem still. Well, that's not working so well, is it? All right, so what do we do? Talk me through this here. Just kind of talk out loud. What's your thinking on this? What would you do first? Say it again. Okay, we need an objective equation. You know, and can we draw a picture on this? I mean, I don't know, kind of, I guess. We're starting with a piece of wire. What did it say? Well, 4 feet long. So there's our wire. And we're going to cut this thing up into a circle and a square. Okay, so if I'm going to make my square and my circle, what would be the variables I would probably need to find the areas of the squares in the square and the circle? How am I going to do this? I mean, what's the area of a square? So x squared, okay. And circle would just be pi r squared, right? Okay, so I'd have to have something like, I'm going to call that x, and I'll call that r maybe, okay? And wherever I choose to cut this thing, let's do this a little differently. Let's set the variable up here to be, because think about what's the thing we can control. And that's always a good idea. The thing you can control, let's assign that as being our variable. What do we control here? We got this piece of wire. We're going to cut it into 2 pieces to make a square and a circle. What are we controlling? What can be varied here on this piece of wire? Where we cut it, right? So where we cut it. So let's do it that way instead. There's a couple ways we could go about this, but I think this is going to be probably the best way. So let's say that distance, that's where we're going to cut it, and we'll just call that x, okay? We're going to use 1 piece to make the square and 1 piece to make the circle. Okay, so we need our objective function here now, which is going to be total area, right? Let's say that we're using, which will be easier? I don't think there's any difference. So let's say we're going to use the yellow piece to make the square. If it has a length of x that we're going to bend into a square, how are we going to turn that into an area of the square? So I guess maybe we should do this. Maybe I should make the square yellow, huh? So there's my square. There's my circle. How am I going to do that? If x is the entire length of that yellow piece of wire, what's the perimeter of the square? X. Okay. So what does that make each side length? X over 4. Okay. Okay, what's the green length of the green wire, if that's the remaining piece of the wire?
4 minus x.
4 minus x, isn't it, right? Because the entire piece of wire is 4 feet long. Okay. So then all of this is 4 minus x. Okay, that's the circumference of the circle, right? So what's the circumference of a circle is 2 pi r, agreed? Right? So then we know that 4 minus x equals 2 pi r. So I gotta solve for r, don't I? Right? So the radius is just 4 minus x over 2 pi. Everybody agree? Okay, and that's r. Okay, so then now we should be able to come up with an objective function, and I'm going to make this substitution, aren't I? When I calculate the area of the circle, when the area of the circle is pi r squared, and I'll use this for my r, and then I've only got one variable. That's good, right? I can calculate the area of the square in terms of x, and the area of the circle in terms of x when I substitute this stuff for r, right? So we get our objective function then. We get the total area as a function of x equals x over 4 squared, right? Plus pi times r squared. And here's my r. 4 minus x over 2 pi quantity squared. Okay, it's kind of an ugly function, but it's not horrible, right? I mean, it's something we can deal with. What's my domain going to be? What are the values of x that I should consider for this function? All reals? Anybody disagree with that?
All positive reals?
Okay, so I could let x be a billion. Okay. I only want 0 to 4, don't I? Because the wire is only 4 feet long. So where the one extreme would be, I could make my cut at 0, which means no cut at all, right? If I make my cut at 0, that means the entire wire would be green. It'd all be used for the circle. If I make my cut at 4, then that's no cut at all. Then I'd use the entire wire would be yellow, and so it's all being used for the square, or someplace in between where I'm cutting it into 2 different pieces, right? Okay. So my domain then, and I'm going to use squared brackets because I could use 0 or 4, right? Those are reasonable things to do. So 0 to 4. There's no x's on the bottom or anything, so I'm no danger of having any undefined values in our domain. So now we just have to do some calculus. All right, so maybe we could simplify this just a little bit here. We could rewrite this as x squared over 16, right? How about this one? Okay, if I were to square this whole thing out, I'm going to get a 4 pi squared on the bottom. Everybody agree? And I could cancel one of those pi's. So I know on the bottom, I'm going to get 4 pi now when that pi is gone. Everybody agree? On the top, I'm going to get 4 minus x quantity squared. So that's going to be what? X squared minus 8x plus 16. Everybody agree? That all makes sense? If I just FOIL out 4 minus x. Okay, so this is really not a bad derivative then to take. We're just going to differentiate term by term. I can split this thing up into separate terms. I could pull the 1 over 4 pi out in front of this whole thing, right? And so what am I going to get then if I differentiate this? What do I get from that first term? Everybody? Good, I get 2x over 16, so 1/8 x. Okay. How about that first term right there, x squared over 4 pi, if I differentiate that? X over 2 pi, everybody agree? Derivative of the middle term, negative 8x over 4 pi. Everybody agree I just get negative 8 over 4 pi, so negative 2 over pi. Okay? And then last term? 0, because it's a derivative of a constant, right? So that's my derivative. How about that? Not very hard. How about while we're at it, let's go ahead and do a second derivative. So I'm just going to get, I don't even need to write down an answer here. What's the sign going to be? It's going to be positive, isn't it? I'm going to get 1/8 plus 1 over 2 pi, which is just some positive. It's a constant positive, right? Okay, so let's find our critical numbers then. So our critical numbers are going to be when this is equal to 0, right? So we got to set this whole fraction equal, or this whole equation equal to 0. I guess we'll do this in a couple steps. So we get x over 8 plus x over 2 pi minus 2 pi equals 0. So I'll just add that to the other side. We good? Okay, now what? Just got to do a little bit of algebra here. What do I have to do to solve for x? Combine like terms, okay? So I do have like terms here, right? I have x times 1/8 plus 1 over 2 pi equals 2 over pi. What should I probably do with this? Sure, but maybe I could simplify that sum of fractions a little bit. What could I do there? How am I going to add fractions? What do I have to do to add fractions? Common denominator. Okay, what's my common denominator going to be? Everybody agree, 8 pi? So I'd have to multiply this guy by pi over pi, wouldn't I? Okay, so I could multiply here. Pi over pi, and I got to multiply this one by 4 over 4. And that's going to give me x times pi plus 4 over 8 pi equals 2 over pi. Okay, and then I'm just going to multiply each side by the reciprocal of that, right? That makes sense? Okay. So we end up with x equals 2 over pi times 8 pi over pi plus 4. And look, we could cancel those pi's and multiply straight across, and I just get 16 over pi plus 4. Okay, is my only critical number. So that is in our domain, isn't it? That's going to be something just a little bit bigger than 2. Okay, right? Because that's 16 over like 7.14, right? That makes sense? Yes, sir.
Well, one, that's going to be a minimum, right?
Well, we'll see. Yeah, I mean, well, you can tell me. Is it going to be a minimum or a maximum? Everybody? It's going to be a minimum, right? Because it's concave up. Okay?
Thinking at the beginning of this, wouldn't you just want to shift all of the thing over to the circle? Because the circle is more efficient than the square.
That's what we're learning from this. Exactly. Yeah. Yeah. So then if we make a table out of this, it's not much of a table. We can probably even just stick it in here. Between 0 and 4, we had one critical number at 16 over pi plus 4. That was a 0 of the first derivative. We got a positive second derivative, so we know that this is a minimum. Okay? And then if we want to know, what are we really looking for here? Are we looking for relative extrema when we're trying to optimize a problem, or are we looking for absolute extrema? Absolute, right? We're just trying to find the biggest and smallest values on our domain. So we haven't done one like this in quite a while, but we know where we have a minimum. Where would we check for maxima then in our table? Endpoints, right? Because absolute extrema always occur either at relative extrema or endpoints, right? So we check the endpoints. If we evaluate our area function at 0, what are we going to get? Well, if I evaluate this thing at 0, here's our area function. That term goes away. I just end up with 16 over 4 pi. So 4 over pi is my area, total area. If I evaluate it at 4, I would get, this is going to go to 0, isn't it? Because look where that comes from. 4 minus x. If I let x equal 4, that term is going to go away. Doesn't it make sense? If we evaluate it at 0, then all of the wire is going to be green, right? So that term went away, didn't it? The yellow term went away. If we evaluate it at 4, all of the wire is yellow. So logically, it makes sense. Yeah, that term goes away, and I get 4 over 4 is 1 squared is 1. Okay, so hang on here. What happened? I got 4 over 2 pi. So that's 2 over pi, not 4 over pi. That should have been. Square. Oh, right. 2. Okay, it's 4 over. No, that's right. Yeah, it's right. Squared, isn't it? Yeah. So it's 4 over pi. Yeah, we're good. Okay. Oh, that's right. I was thinking the other way. We want the circle. That makes sense. And this is 1. Yep. This works. Okay, so our maximum is going to be here, isn't it? Our absolute max is right here. How about that? Okay. So if we wanted to minimize, what is this? This tells us something kind of interesting. It talks to us about the ways, how the most efficient ways to encapsulate area, right? Okay, so if we want to encapsulate area efficiently, if we want to have the maximum area with the minimum perimeter, total perimeter, we're going to use the circle, right? If we want to have the least efficient way, if we want to have the most perimeter for the least area, we split this thing in the middle somewhere, right? Okay, makes sense? Okay, so we could, this is interesting, but it doesn't really apply so much to our universe, which is 3-dimensional, right? We have 3 extended dimensions. And so this is a 2-dimensional problem. It's got some mathematical significance, but what if we were to kind of extrapolate our thinking here into 3 dimensions? What would the analogs be? And we're not going to get exactly the same result, but we're going to get similar results. You can make a generalization here. So if we were to do something like, it's a much more complicated problem to do mathematically, but we can still make this extension. If we were going to extend this thing to 3 dimensions, instead of a piece of wire forming a perimeter, what would we probably have instead? Okay, like a sheet of fabric or something, right? So we've got some kind of a skin that we're going to put over the outside of an object, okay? What would these shapes be? Instead of a square and a circle, they would be sphere and a cube, okay. And so this is telling us then, if we extrapolate to 3 dimensions, this tells us that the most efficient way of encapsulating volume is what? A sphere, right, okay. So why would that be important in, let's say, the animal kingdom? Where would you have an object or an animal that would need to really efficiently enclose its volume? It would need to have minimum surface area for maximum volume. How come the ocean?
More buoyant, maybe?
Okay. I mean, maybe, but think environmentally. I mean, you can see in the ocean, there are creatures of all different shapes and sizes, right? But if let's focus on mammals. So warm-blooded animals, right? They have to maintain a constant body temperature. Where would you have some extreme conditions that might cause you to want to minimize your surface area?
Really cold.
Really cold, right? Does that make sense? Places that are really cold, where are you going to lose your heat? Heat's going to be transferred through your skin. So how do animals combat that? Well, they have insulation, right? Mammals that live in the ocean would have layers of blubber, right? But what's the other thing they would do? What would their shapes evolve to be? You'd want kind of rounded shapes. And now think about, if you look at the mammals that live in the extreme cold climates, our calculus really just explained this. If you look down in this extreme southern Atlantic or up by the, in the Arctic, what do you see? You see extremely large whales that are, they're kind of whales, right? I mean, they're big and sort of, they're not exactly spherical, but they're kind of oblate spheroids, I guess you could say, right? You see walruses and you see seals and you see all these different kinds of animals, and they all have that same general shape. The warm-blooded animals do, right? Cold-blooded animals don't need to, but the warm-blooded animals have to be able to conserve their body heat, and so that's what they do. Interesting, right? So you have more rounded, bulbous, and what about the size? If you look at, so if you were going to look at the size of a sphere, does it make any difference? Or does the size of a sphere have any impact on how efficiently it encapsulates volume? Think about that. It does. What you're nodding your head, Melon. You're right. What do you think? What's your thought on that?
I don't really know.
Anybody have an idea? Okay, so bigger is better or worse? Bigger is better. Better, right? Because volume grows. Let's look at this. If we look at the volume and the surface area of a sphere, right? Volume as a function of r is 4/3 pi r cubed, right? So the volume is growing as the cube of radius, okay? Surface area equals 4 pi r squared. It's only squared, right? So if I take animals, let's say I double my radius. I've got some certain size, and should I grow bigger or not? Do I want to double my radius as an animal? If I double my radius, I am increasing my volume by a factor of what? 8, right? 2 cubed. Everybody see that? If I double my radius, I'm only increasing my surface area by a factor of 4. Okay, so I'm encapsulating, if I double my radius, I'm encapsulating twice as much volume per surface area as I used to. Everybody see that? So there's an imperative here. There's an evolutionary imperative to try to make things big also. Well, are animals that live in the extreme cold oceans big or small? They're big. They're real big, right? The biggest animal on Earth is a blue whale by a significant margin. Look at walruses and sea lions, and these are multi-ton animals, or big animals, right? Okay. So that makes sense. Okay. What about the opposite extreme? Would there be a place on Earth where mammals would want to do the opposite? Africa, for example, right? You got a place that's really, really warm, then what would you want to have efficiently encapsulate surface area? No, you want to do the opposite because you want to be able to transfer your heat away, right? You don't want to overheat. So, animals have evolved different ways of doing that. Humans are great at it because we sweat. We have lots of skin exposed. But in general, animals that live in really hot climates, then we should expect them to have very inefficient coverings, right? They want to have low volume to surface area ratios. Well, think about the animals that live in Africa. Do they have that? Well, giraffe, gazelle, they're all, or they're small, they're tiny little animals that they're kind of jagged. If we wanted to ascribe like a pointiness index to animals, where the pointier, the higher the index, you would say that there'd be a very low pointiness index for cold water dwelling mammals. They don't have many points on their body, right? I mean, they're pretty large and bulbous. Animals that live in extremely hot conditions would have a high pointiness index. Like a giraffe is all elbows and knees and necks and things, right? I mean, so what's the elephant in the room here that seems to do the opposite? The elephant. There you go. Yeah, the elephant. So, but the elephant is massively cheating, though. How is he cheating? He got these big radiators, got these big ears, right? So the elephant, that's kind of a stray data point that we can just toss because he's cheating so badly. He's got these ears that increase his pointiness index massively, right? Because they're these big radiators, okay? And then, right. And then like a hippo, he's kind of cheating too because how come? He's always in the water. Yeah, exactly. So what's that? Rhinoceros. Big ears again. Yeah. I guess they're not that big. Yeah, rhinos are kind of, I guess they're sort of an anomaly a little bit. They're a little bit of an anomaly. Yeah. But in general, like if you look at most really hot weather animals, they're very small too. Very small. Like even in the desert, you'd see most of the little mammals you'd see just scurry around, and you don't see them on the documentaries because they're not very glamorous, but they're pretty tiny. Okay, so I don't know, kind of interesting that you can take a stupid little problem about wire and bending wire, and it gives you a little insight into even why animals have the shapes that they have. So if we were to look, this is probably a little further than I needed to go with this, but I just think this is kind of intriguing. So why a circle? Well, if you take the area of an n-sided regular polygon, so what's a regular polygon mean? Okay, all the angles are equal and all the side lengths are equal, right? So it'd be like a square, equilateral triangle, regular hexagon, etc. Here is the area as a function of side length and number of sides. Okay. What is this thing here? I can't remember. When I made this, can't remember what I was doing here. I know it was really cool. I wouldn't have done it, but okay. And so the perimeter then would just be S times, I don't know why that was so significant. The perimeter is just going to be the side length times the number of sides, right? Now, what did I do with it? I know I did something with this. Better be good. Let's see. So if we look here at the areas, just in Desmos, if we look at the areas of fixed perimeter regular polygons then, here's what you get. If we take this expression where X is the number of sides and P is the perimeter, okay, then I'm just setting P to be 10 arbitrarily. Then look what you get. As the number of sides goes up, look what happens to the area. Hey, it makes sense, doesn't it? The area goes up, and if we were to extrapolate this out very, very far, as n approaches infinity, what shape are we approaching? A circle. Yeah, so if we go far enough out there, if the perimeter is 10, if we go far enough out there, we should start to see values that look like the area of a circle with a circumference of 10, which we would, right? Okay. Anyway, just kind of interesting. Okay, what about this guy? This is another, see if we can at least get this one started. So if you've got two light sources that are separated by some distance, right? They're 12 meters apart. One of the light sources, the intensity is 5 times that of the other. So it's a 5 times brighter light, okay? Well, we know that the intensity goes as the square of distance, It's the inverse square law, right? So if you double your distance from a light source, you're decreasing the intensity by a factor of 4, right? It's inverse square law, 1 over r squared, okay? Well, where would you obviously go if you want to have the brightest light? Right next to the bright one would be the brightest you could get, okay? But the question now is, where could you go on the line between those two lights and have the least intensity? Okay, what's your gut telling you? What do you think? Just in general, where do you think you're going to want to be?
Very close to the weak one.
Away from the bright one.
Away from the bright one, but do you want to go right next to the one that's not so bright? No, because the intensity, still, it's a 1 over r squared law, right? If r becomes really small, the intensity is going to get very high next to either one of those lights, right? So we're not going to want to do that. We're going to want to distance ourselves from the lights. On that line, though, our intuition probably tells us we want to be a little bit closer to which one? The dim one, right? Okay, but we could find out. So let's see if we can set this up here. So we got to come up with an objective function here, right? Which is just going to be, and that's intensity is what we're trying to minimize, right? If we want to say this, restate the problem with using minimum or maximum, we would use the word minimum. We want to find where is the intensity at a minimum, right? Okay. So how can we come up with an expression then for the intensity from the weak light? There's some math I really want you guys to get used to here. Here's the key statement. Let's read through the whole thing. The intensity of a light source at a distance is directly proportional to the strength of the source and inversely proportional to the square of the distance from the source. Okay? 2 light sources, one 5 times as strong as the other, are 12 meters apart. At what point on the line segment joining the sources is the intensity minimum? A minimum, okay? Yes, sir, what do you?
We can make the intensity on the light 1, 1, and then wouldn't it just be 1 over x squared, where x is the distance?
Okay, so we're going to know, so if we're saying, let's make a picture. So here are our sources, right? Here's the strong source, is this point right here, and here's the weak source right here. And we're somewhere on this line in between the two, right? Okay, so what's the thing that we control here? Okay, where we're gonna be, right? So what are we gonna define our variable as then? Probably x, right? X is just gonna be this distance, like from there. Oops. So it's going to be, we'll know it'll be probably a little closer to the strong one. So we'll make it somewhat realistic. So it's going to be something like right there. That's x, right? So if we want to come up with some expression for the intensity, it says it's proportional to the strength. So we'll call this I sub s, the intensity of the strong source, right? It's proportional to, get it next time. Well, actually, we'll wrap this one up this afternoon, and then it won't take very long, and then that'll be it for the afternoon.